recording. Okay, guys, quiet, please. Thank you. So E is called Euler's number. It's kind of like pi. We have Pi Day, obviously, on Tuesday when the weather was really nasty. Euler's number is this. Well, I didn't do Pi Day with you guys, but anyway. Yeah, it's kind of a weird number. It's called the natural base, in case you're curious, or the natural number. Where it came from, here's where it came from. So next I'll show you how you discover this number. Actually, I'll show you now how you discovered it. It's kind of a strange phenomenon, but if you have like something like this here, 1 plus 1 over n raised to the n power, and assume n approaches infinity. Well, let me show you right now. Let's get. Let me get.
It's a number that's close to
Infinity. I'll show you right now. Yeah, let me do this, guys. This will be a good demo here. I'm gonna do a calculator demo right now. Let's go to math department. So this is my graphing calculator app.
On the calculator.
Says what? Sorry. That's scientific notation, but when it gets really large, yeah, sure. Yep. But that's a different E though. That's more scientific notation. So let me resize that. There we go. Perfect. Okay. So what if I did 1 plus 1 over 10 raised to the 10 power? You get that, right? Let me repeat that. Let me change that to, say, 100. Now, what's going to happen is that the base is obviously, the fraction is smaller inside, but the exponent's larger, right? So there's a trade-off, right? The base actually gets smaller because instead of doing 1 plus 110, doing 1 plus 100, but the exponent gets bigger. So it increases, but not by much, right? What if all of a sudden I increase that to, say, 100,000? Let me insert 3 more zeros. 1, 2, 3. And 1, 2, 3. So it didn't increase that much, even though I made the exponent much larger, but the base got smaller. Yeah, so it gets very close. And if I hit E, second ln is where Euler's number is located. You see, they look pretty close together. Let me do this one more time. Nope. Let's try again.
What if you did E times like E exponent?
The E, what? E to the 2 power? We'll just keep increasing because you're squaring it, but let me add 3 more zeros. 1, 2, 3. That's 100 million. 1, 2, 3. See, it kind of looks like that, and E is pretty close together. Like they only differ in the last 2 digits there. So that's what E is. It's some guy named Euler kind of discovered that 1 plus 1 over n. We raise the n power. If you can make n really large, it ultimately converges to a certain number, and that would be E. There are actually some scientific applications that use E, some sort of naturally occurring things that kind of follow this model. So that's why it's called a natural number, because there are just some things in nature that, like, for example, if you're looking at compounding interest actually, I know they didn't have interest back in the day, didn't have the bank system we have now, but it kind of follows this pattern. So that's what E is. It's just a number that converges to that. But the math here is going to be really easy. The math is going to be just a lot of review from what we did on Wednesday, as well as just review from previous units. So, like, for example, for the first problem here, you're asked to simplify. Think of E like a variable. That's what I'd say. Think of E. God bless you. Think of E. Yeah, totally. Yeah. Think of E like a variable when simplifying. Let me write that nicer. Sorry about that. When simplifying. So in this case, that's E to what power? That's going to be E to the, that's it. That's all. Or if you simplify this one, what do you get?
E to the 1.
And a 4. That's it. Or for C, Yeah, so you get 25. Oh, sorry, 25. Yep, thank you, Hugo. That's all. It's honestly, the problems are pretty simple for this lesson. What underneath, sorry?
The negative exponent.
What do you mean by underneath? I don't understand.
Like 25 over E.
Oh, I see what you're saying. No, I don't care. Oh, I see what you're saying now. Putting below a fraction. No, I don't care. So anyway, that's all you're doing. And then second question is just using a calculator, which I know you guys can do. So let me pull up my calculator again, which I don't know why I closed it. That was dumb.
Will you be allowed to use graphic?
Yeah, for some problems you have to because
But will we be allowed to put like on test?
I haven't thought that far ahead, so let me get back to that. That's totally not on my radar right now, but I'll let you know. But yeah, some problems you at least need a scientific calculator. You just can't do it otherwise. Hold on. Why is it not opening?
Oh, it sounds really complicated. See this.
Hold on. Oh, there it is. Okay. Hold on. I got too much stuff open here. Hold on. Unpin. Unpin. Okay, much better. Here we go. So yeah, sorry guys, I'm just struggling here. Okay, here we go. Guys, quiet. E to the 4. Just that. There we go. It's not that hard, right? 54.598. Sure. Yeah, I'll tell you how to round it. I mean, it's such. I mean, again, this is just very basic stuff. The whole point of the second example here is just so you know where to locate E in the calculator. That's the whole point of this example. Like, if you want E to negative 0.09, plug in the calculator, right? Let me go ahead and hit E to negative 0.09. And there you go. That's all. Nothing too crazy.
Wait, where do you find E on the calculator again?
Great question. I should have wrote that down. I did mention it, but I glossed over it. Second ln. There we go. ln. How do you get E? ln's on the far left, lower left corner. Now ln stands for natural log, which we won't cover until after spring break. What was that? Second ln. Hit the second button, then ln. ln should be right above store. It's on the far left side. It's a third. It's lower left corner, but third. Yeah, cool. All right, that's all. Yeah, that's the whole point. I want to want you guys find. Okay, let's move on. All right, now graphing. Don't freak out with graphing.
God,
Some people will freak out.
I'm freaking out.
After this, we'll do some word problems, and then we're done with the lesson. Okay, so this is what? Sorry, there's 3. No, 2 word problems. I think no, it's 2 or 3. 3 word problems. You guys will be fine.
Is this like the exponential growth stuff?
It's the same thing. Yeah. So here's the deal, guys. E to the x is like this.
It's like a parabola, or no, it's not.
It's just a curve.
It's like you guess.
All it is, guys, quiet, let me talk. All it is just your doing an exponential function. So, Patrick, thanks. I know you're explaining, but I've seen you talk. It's just exponential growth. That's all. That's all it is. So I'm going to plug in 0, 1, and 2 so you guys see what's happening. I'll do -1 also. So e to the 0 power, anything to the 0 power is always 1. We talked about this. Anything to 0 power is always 1. 1 to, if you plug in 1, that's just e, which is roughly 2.7. Sure. That's e squared, which that's a little tricky. I think it's roughly 8. So if I do e squared, I would never ask you to do this without a calculator, obviously. That would be 7.389. It's gonna be a rough estimate, and then that's e to -1, which is 1 over e, which is 1 over 2.7 roughly. which is what? E to negative 1.
0.36.
Yeah, 0.368. Yeah. We won't do e to negative 2 because I think you guys get the idea of what's happening here. So I plot the points. I'll do green. Always gonna have a point right here. Then you have
What number? Oh,
0, 1. And then 2.7, obviously it's between 2 and 3. You don't have to be so precise. Like if you like put it like right here instead of like right there, I'm not gonna care. It's not a big deal. Just put somewhere between 2 and 3. 7.389, that's probably over here somewhere. And then negative 1 comma 0.368. It's like that. So you have these 4 dots, and I'll connect them. And there you go. That's it. The domain is still going to be all real numbers, just like any exponential growth function, right? Right, it's no different. The range, if you take a look at it, you're raising e to some power, right? So e is positive. How are you going to take a positive number and make it negative? You can't, right? How can you multiply a positive number over and over again and make it? You can't. So, right, it's going to be the same thing as before, from 0 to infinity.
Wait, you're not putting bracket on this?
No, because it can't exactly equal 0. Yeah, you can't exactly equal 0 because in order to have a power equal 0, you need 0 as a base. But your base is not 0. Your base is e. So it's impossible for that to happen. And there is I talked about asymptotes in the last class. So I'm glad I'm doing this because this might reinforce things that are in the Zoom call on Wednesday. This is called a horizontal asymptote. It's like an end behavior. Yeah, totally. Because when we do logarithms in the second half of chapter 7, there's asymptotes, and then chapter 8 is all about asymptotes. So yeah, absolutely. But it's not hard. It's not hard. Yeah, and I'll tell you right now, the asymptote is always going to be the vertical shift, like whatever number you're adding to the end of it. So let's do this, guys. Let me go back to my graphic calculator. Let's say if I typed in e to the x, right? If I come on, let's do it again here. Sorry about that. Second ln e to the x. Okay, there's a graph, right? Graph looks like that. If I were to do this and put a +2 at the end of it, but not in the exponent part, but outside of the exponent part, what do you think the graph's going to look like now?
shift right.
Shift 2 up, because I didn't do it to the exponent. I did it to the outside. So Isabel, to answer your question about asymptotes, really just looking at what your number you're adding to the outside. So like if I have like a 2 on the outside, my horizontal is y = 2. If I do a -2, what's going to happen now?
Just gonna go
2 down. So 2 down. No worries, it's all good. It happens. So that's all that happens there. So nothing too crazy. So that's that graph. Now, we also asked, yes, Ron, go ahead. Sure, yeah, totally, yeah. You can, go ahead, no problem. Let's look at this one here. Let me make another table. We'll probably just do on the same coordinate plane. So let's do 0, 1, and -1. I think just 3 points is good enough. So that's gonna be still e to the 0 power. I'm doing the second equation now.
This is like a graph.
Yeah.
Second graph.
Oh, it's a second graph. I'm sorry. Sorry. Duh. I put a second graph here. Thank you, Matthew. I appreciate that. Matt knows what's up. All right. So
Big guy.
he's got a better bracket than I do too. My bracket's terrible. Yeah. Did he have a second chance? I want a second chance bracket. All right, here we go. So I'm just gonna plug in 0, 1, and -1. See what happens. It totally, yeah. You can at least use a scientific calculator for this part. Yeah, totally. Yep. Yep. E squared was that was like 7.3, I think, right? Yeah, let me go back to the calculator. E squared and -2. Okay, 0.13589. Okay, so when I plug in 1, I got 0.135, so it's down here somewhere. If I plug in 0, I get 1. Plug in -1's way up here. It's up.
So for each the negative second, that is 1 over.
Squared, right, which is 0.135. Right.
Oh, so it's just flips.
It is flipped. That is right. So what happens here, this now becomes exponential decay. The reason why is that you have e to -2 raised to the x power.
I don't -7.8.
It does positive 7.38. I crossed my 7s.
Oh, sorry.
No, I crossed my 7s.
Yeah, would domain and range be different at all?
No, they'd be the same. They'd be the same. Great observation, Charlie. They'd be totally the same. Yeah, that would not change one bit. Unless if I added a number to the outside, then it would shift horizontal. Sorry, shift vertically, and the horizontal would change. Now, why is this decay? What if you factor out the x from the exponent? So put the x out, which makes sense because e to -2 raised to the x is the same thing as e to -2x, right? Well, what is that? That's 1 over e squared. And 1 over e squared is definitely less than 1, right? In fact, it's between 0 and 1. And so whenever the base is between 0 and 1, that's decay. So that's why you see a decay function with this. When you simply switch x from a positive to negative, because the base was greater than 1, but because of the negative exponent, it flips it, making a base less than 1. So yeah, go ahead. That was growth. Because the base was bigger than 1, because he had e, but because he had e to -2x, if you focus on the e to -2 part, that's less than 1.
So, and it's going to the left, so it's decay.
Yes, exactly. Because as x gets bigger, y gets smaller. Right? If you make x larger, if you keep plugging larger numbers for x, right, right, right. Yep.
I'm assuming for those.
Well, yeah. We're gonna talk more about this next week for sure.
No, we're actually just learning this.
Well, yeah, well, sometimes you.
Sometimes you don't. It's true. Okay. All right. So anyway, you guys will have a chance to do classwork. Guys, quiet. You'll have a chance to do classwork on this on today, and then next week. Next week, I'm not doing any new material. We're just going to keep doing more review of this stuff. So,
Wait, is the test?
it's gonna be on Monday of Spirit Week.
Yeah, but like, is it, what is it? Is it 1.7.1 to?
7.3. That's all. Right. So small.
That's
Only this?
Yeah.
That's
The 7172.
Oh, yeah.
Right.
It's not next week.
Correct. It's very soon. 2 weeks from today, we start spring break. It's exciting. Okay. 2 weeks from now. Today, on the 31st. Today's the 17th.
And is it gonna be like bigger grade book or small?
Small. Okay. Number 4. Now we're gonna talk about word problems. Now these guys, quiet please. Charlie, Matt, thanks. Okay, so these word problems, I'll give you the formulas. Don't worry, because the formulas are kind of hard to remember. So this is dealing with interest, which is actually interesting. No pun intended, by the way. You get that? No, no. All right. No, interesting because what happened last Friday, guys? You guys remember what happened last Friday? SVB collapsed, right? And at First Republic now has to be bailed out by the government.
Uncle was in there when FDIC came in and seized it and renamed it, like they all.
Oh, really? That's crazy. So anyway, it's good to understand where your money is, because if your money's tied up, you can't get your money out, you're in big trouble. So trust the bigger banks like B of A, Chase, Wells Fargo. Even though,
Didn't they buy the bank?
well, yeah, no, the government will, like, if you have, because I mean, so if you go all the way back to the New Deal with FDR, like everyone's insured up to $250,000. But let's be real here. People around here have like a lot of more than $100,000, $250,000. Some people have $100 million in the bank, right? So
their payroll or not. Like my uncle owns a bio, like CEO of a biotech,
Mhm.
and he's able to make payroll, but a lot of other.
Well,
biotech-
even a school like this, I mean, we use a bank like, we don't use SVB, but we use a bank like SVB. Like, what, right. No, yeah, I know. We use First Republic, right? I mean,
Our Spanish teacher would talk.
yeah, no, if I couldn't get paid, that would suck. So, yeah, I don't know, maybe.
They bought it for $1.
That's a good
Like,
thing.
But everyone's money is safe though. I think that's the most important thing. Yeah.
Like, but it's and they, like, if they gave it.
Yeah, that the mechanics I don't know. But anyway, so let's talk about, that's more exciting, but let's talk about this that's a little more boring. So here's the deal. I might even tell you what these things represent. Let me get back to you on that. But A represents the amount of money you have. P, principal, guys quiet. Principal is how much money you started with. R is your rates. T is time. And N is the number of times your money is compounded, meaning how many times the interest is applied to your account. So how many times the bank actually will update your account with more money. Now, this is a very simple interest. I think the more interesting one is looking at mortgage rates or finance or like investments, like a retirement account. Those forms are too complicated for this class, but maybe in pre-cal you'll do it.
They do an APP card.
I think so. I'm not sure. So anyway, let's go over this problem, guys. How much money are you guys starting with here? Guys, how much money are you starting with? $4,000. What's my interest rate? So you got to put 0.03. Always for interest rate, you divide the percentage by 100. Okay, always divide by 100. Time is 4. Now compounding. Quarterly means 4. How many days in a year? 365.
No, days in a year.
Hold on. Let me. This is a little confusing.
That's why I was like, why is there
It's
4,000?
0.25.
No, that was a comma and a separate number. Let me do this. 365, except the leap year. Right. Quarterly, yep. Now, continuously, you can use this formula instead. Continuously is when every waking second, interest is being applied to your account. So you're always getting interest. As I'm talking, interest is being put in my account the whole time. Super slowly, exactly. Yeah, totally. Yep.
Will you write those?
What's that?
I might. I haven't decided yet.
Should we just plug it in?
Oh, come on. You're right. It won't matter. You're right. So let's do the first one, guys. So you do 0.03. 4,000. Are you talking right here? 4,000. Oh, maybe Patrick's head's in the way. Okay, sorry. Okay, so it's 4,000 times 1 plus 0.03 divided by 4, to do quarterly, and an NT 4 times 4. The exponent's NT, so N is 4 and T is also 4.
And what was 30 and PE?
You'll do 365 times 4.
Oh, E is the.
So guys, let me work this out first, and then we'll do it again. So what? Sorry, that's a different one. We'll get there in a sec. No, because it's only quarterly. So guys, quarterly, you're using this formula here. Okay. We're gonna use this one for quarterly and daily. Let me plug in my calculator. Let's do it right now. So 4,000 times parentheses 1 divided by, sorry, 1 plus, my bad, 0.03 divided by 4 raised to the 4 times 4. Or 16, sure. So you'd have that much money left
Into your money.
after 4 years. Well, yeah, because you're getting interest, right?
Oh, I thought that- The one that's taking.
What about something called?
No, no, that's if you're paying
That's like
a loan. That'll be a loan. That's a different story, right? So obviously you could do better with your investments. I don't think this is really a great way to invest your money, but if you did put your money into an account that had simple interest or annual interest, sorry, for 3%, and it's compounded quarterly, that's how much money you'd have.
For the investing.
I don't know.
Nothing. What if it's just a bank account that pays it?
No, 4 times a year. No, no, your money. So basically, your money's being updated. Your account's being updated 4 times a year. So 4 times a year, they're applying this interest. But this is how much money you have at the end of 4 years. At the end of 4 years is how much money you'd have. Let's do another one. Let's do another one. Let's do quarterly. Sorry, let's do daily. Sorry, daily.
Oh, that's what
Why is
you
it
need.
Let's do daily now.
Oh, no, it's RT now.
If I do daily, okay. So we erase this now. Yeah, a little bit in the classwork so you can practice it. Because now we're doing it daily.
So we have to do two different, quarterly, daily, and continuously.
Right. We're doing 3 different
It's just like 2 problems in one.
it's actually 3 problems in one.
So if it's continuously, then just consistent.
So I'm going to
You only make
do this again.
$2.
You don't make that much more, right?
You only make like $2.
If it's continuously,
So-
then you continuously. update it with 5%.
But the base is much smaller though.
Divided by 265.
So you don't make that much more if you do it daily.
Continuously, what do you divide by if it's continuous? You divide by.
I just.
Yes, I'll talk about it in a sec. Okay, so guys, for daily, it's not that much different, right? We did make this lower. This overall base became lower, but the next one became higher, but it's a trade-off, right? So the base is 1 plus this number. This fraction got smaller, because I made the denominator bigger. Okay, the exponent bigger, so it's a bit of a trade-off, but yeah.
You need like $2 more.
Because it's a trade-off, because the exponent got bigger, but the base got smaller.
It's not.
Now, if you do it,
Because it's
Mhm.
Similar to.
it's
What was that?
something like-
yeah, better, but not much more. Not much more.
$2. $2 can buy, actually, $2 can
I
buy.
don't get how this works.
You're just plugging into a formula. That's all we're doing. It's just plug and chug. There's not much more. There's not really much to understand.
Plug and chug.
It's just plug and chug. That's what we're doing.
That's my jam.
Plug and chug. I like that. All right.
Last time he plug and chugged, he ended up.
Uh-oh. All right. Now. Okay. I'm not sure what that means, but let's keep moving. Now, continuously. Continuously mean n is infinity.
Sure you.
Okay. So you got to plug in infinity here. That's what continuously means. However, how do you deal with infinity, right? So what you do is that all this becomes E. Just like we said earlier on, that E is this number that follows this pattern. So when you do continuously,
Then it's RT into.
you can use this formula instead.
Then it's rate.
Yeah, so you can do 4,000 times E, and then you're going to use R, which is 0.03, multiplied by 4.
So you can use it either, is that what it is? Or is that only for continuous?
Continuously kind of takes care of the infinity part for you. So it's just more accurate.
So if you technically use.
You could plug in like a million. If you plug in like a million, you probably get the same thing.
So if it's not continuous.
I don't even know.
Right, right.
Just like.
Yeah, this is only for continuous guys, this formula here. So I'll work this one out really fast. 4,000. Can you lower your laptop, Matt? Yeah, that sweater's not hiding anything, dude. All right, nice try. I promise you I will. Are they, wait, is UCSB in the tournament too? Who are they playing? Baylor, okay, I have Baylor win that one, so.
Have UCSB.
Why not? Why not? Let's see. At this point, I don't care. I want chaos. I want everyone's bracket to get busted. At this point, so Yeah, not that much more, guys. It didn't go up that much.
You're still number one.
And Ted-
That's why you have a George. Are you still number one?
So here we go. And guys, quiet, please. Thank you.
Somebody's just like.
So you see here, the difference, the difference. Guys, can I talk, please? Thank you. Thank you. All right. The difference is only about 2 cents, so it's not that much different. So as you make n really large, it doesn't really make much difference. So anyway, let's move on to 2 more word problems. We're done. Okay, these next 2, again, I'll give you now these I think are a little more interesting because, and actually you could probably use like COVID to I might make a problem with COVID because COVID, we dealt with infection rates, and infection rates were increasing like very fast. So you could use exponential models to understand how COVID was working. But let's talk about cigarette population. In 1990, there's about 300. I think this is about right. I think there's about 300 students here in 1990. And obviously, this is a dated problem because now we're in 2023. But we'll just go with it. Let's go with it. So here's a formula I'm going to give you guys. The formula is going to look like this. It's not that much. It's not that much different, but it's a little different.
So we're not using the same one.
No. So A is going to be the initial amount. R is going to be the percent. The percent. We'll say percent change. And T will be time. Okay. So, if you look at it right now, we know that we have, what's my initial value here? 300. What's my rate or my percent change? So 0.03. And how long am I doing this for? 22 years. Now, why? Because that's 2012 minus 1990. Right? 22 years have passed from 1990 to 2012. So that's just, again, it's plug and chug, which Cam knows all about, right? Sorry.
I cut through my finger with an X-Acto.
That's what happened? Okay. All right.
We were doing the plug and chug. I plugged through my finger.
Sounds awful.
Kind of sounds like a skill issue.
All right. Okay. I don't know what you're talking about. Yeah, dude. All right. Yeah, I was like, I saw a little flashback. What's going on? All right. Well, you know you're in school.
But that's actually like.
Oh, you're looking for a job? All right. All right, here we go. Oh, sorry, I forgot to put the parentheses here. Okay, so guys, quiet, please. So this was the population in 2012. And actually, I think it was pretty close to that. I think this is a pretty good model. So about 575 students were at Sacred Heart in the year 2012, assuming that the school grows by about 3% per year. As the school grows, we get more buildings, we hire more teachers, we get more athletic fields, all that stuff, right? Yeah.
So for the T, for the time, oh, you just did the difference.
Difference between the 2 years, exactly. Yeah. Actually, let me be a little more clear about this because I kind of glossed over this. It's time in years after 1990. I should be a little more explicit. So my apologies that I was so vague. I should be more explicit and tell you how much time is being passed. So in years after 1990. Okay. Now, let me pose this question to you guys. Is this a good model to use for the next 30, 40 years, would you say?
No.
Why not? Go ahead. I'm curious to hear this. This is good.
Because I don't think that
Mhm.
the school's gonna be able to hold.
Yes.
Like
Thank you.
800 people.
We could, but then can we get away with charging the money that we can when you could go to like St. Francis for half as much as just many students, right? Or Sarah High School or whatever. I mean, why do we charge as much as we do? Because we have small class sizes, right? Like we don't go past 20 students, right? We have because No, we want to give higher quality teaching. Yeah, well, that's a different kind of, so guys, let me finish talking. So what Patrick said, is there a cap, guys? There's a cap to this kind of graph. Not these graphs necessarily, but there is another type of function we learned pre-calculus called logistic function, which does take that into account. Like COVID rates, right? Like, sure, COVID can keep increasing, but after a while, everyone gets COVID. And that's that, like the population of like, say, Redwood City, let's say, is like, what, almost 100,000 people? Like, at a certain point, you reach a saturation, but everyone has COVID, right? You can't just keep. It would affect the range also, would, totally. Yep. But let's do the second part here. When would the population be 800? Let's look at that one. Well, so what you do, yeah, let me do this again. You do 800 for Y, 300 for A, 1 plus 0.03. Do I know the time? No, that's what I want to solve for. Now this problem right here. No, you can't. Now, this is, guys, I really need you guys to focus. I know you guys are a little squirrely, it's Friday, I get it, but let me, this is very important. When we solve for T, you can do it two ways. You can solve for T two ways. One way is algebraic by isolating T, but I haven't taught you how to do that. Yeah, that will be the second half of chapter 7. And will require a log, nope. This is something you haven't learned yet. Logarithms is the second half of this unit. It's probably one of the most important things we do this year. We're not ready for that yet. We'll be ready. Probably, I might introduce you in Spirit Week, but definitely after Spirit Week, we'll talk about it. Yeah, but you're gonna get a deeper understanding of it. Or you can graph on Desmos or graphic calculator. Okay, I'm gonna do it in Desmos to make it easy for you guys. Okay, so here's how you do it in Desmos. Actually, I should do it in the graphic calculator. Let's do it in the graphic calculator. Okay. So this will be good because now you have a video to watch on how to do this. If you have a graphic calculator, you can follow along. Maybe what we'll do next week, we'll do a graphic calculator demo. So I'll probably ask you guys, everyone bring a graphic calculator, or I'll bring some from the other rooms, and we'll practice. But yeah, I don't want to do Desmos because it's too easy. I know you guys can do it in Desmos just fine, but on a test, you don't have Desmos. So here's what you're gonna do, guys. You won't have a laptop, yeah. So, okay, guys, please, I need you to focus. 2 equations you're gonna make. You make 2 equations. You can do 300 parentheses 1 plus 0.03 or 1.03, same thing, raised to the x power. Down below, you can do 800.
Wait, how do you just do that?
Hit the right below node. See X right below node.
Why are you doing it?
So what? So
Why is it? Because Y is,
why? What do you think?
that makes sense.
Okay, the second graph.
And it's showing when they
Okay,
intersect.
guys, quiet. The second graph. What do you think that graph's gonna look like?
It's gonna be a bar, like a line.
It's gonna be a horizontal line, exactly.
Intersects, that's-
Yes, you're looking for a point of intersection between these 2 graphs. However, if I hit graph right now, I'm not gonna see it. This is the problem with the graphing calculator.
It's too big.
What do you think the bounds are for this graph right now? For what?
20 or something.
It goes from -10 to 10.
Yeah.
And -10 to 10.
I guess.
Go ahead, Isabel. You can set the bounds, yes. So if you go to window, now this is a skill that, guys, quiet please, we will have to do next week because I want to make sure we spend a lot more time on how to use graphic calculator. What does X represent in context of the problem? What does X represent? No, in context of this word problem, like what is it representing? Time. X represents time in years. How many years are we talking about? Probably maybe 20, maybe 30, maybe 40. Well, in 22 years, the population is 575. So it's probably much more than 22 years.
It's 575 to 800.
But at the very least, do I want negative time? I don't have a time machine, not going back in time, right? So, but let's go 50 years. Let's go 50 years, see what happens. Okay, why? Y represents the school population. Is the school population gonna be negative? No,
800.
but we want to get to 800. So let me do 1,000 just so I'm high enough. And now X scale means every tick mark, how each tick mark is separated. Let me do 10. I mean, that won't matter for the graph, but just so I can see the tick marks spaced out better. And I'll do like 100 here. Just because I don't want 1,000 tick marks, right? From 0 to 1,000. Let's do like 100 for every tick mark. So now let me graph. Here we go. So there's the exponential function, right? And then let's wait for the horizontal line. Okay, there we go. I want to see where they touch. Yeah, well, actually, here's what you do. If you hit second trace and select intersect, it'll find the point of intersection for you. You move close to the point of intersection. It says first curve, which is the exponential function. Just get close to it, hit enter. Second curve, I'm on the line. Just get close to it, hit enter. Ask for guess, hit enter again. And it'll give you the answer.
But how do you do it?
I'll do it one more time.
832.
So it's about 33.18 years. Or the year 2023. Yeah, I'm gonna do it again right now.
But we're not at
Bro, when you control.
Obviously, we're not 800 students, right? We're at 650 students. So yeah, we're not at 800 students.
Did you say like 34 years?
Sure, or 33 years. It's that I don't care too much about, like as long as you're close enough. But let me walk you guys through it one more time. Let me go in clear. Let me go back to the home screen. Okay, so what did I do? I had this equation I had to solve, right? This is the equation I had to solve. 800. And by the way, you could do this for any equation in anything you do in math. This technique, it will work for any equation that you want to solve.
Why do you have to be so close to it?
You don't have to, but if there are multiple points of intersection, then the calculator will get confused. So you have to
It's like closest.
yeah, exactly. So 1 plus 0.03 raised to the t power. Okay. So here we go. Let's punch it in again. So I'm gonna clear this out so you guys can see me do it from scratch. So what you do is this: you let one side be y1. Come on, clear. There we go. Let one side be y1. Let the other side be y2. And use x instead of t. That doesn't matter. So I'll do 300 times 1.03 raised to the x power. Right. Next step, I'll do 800. And let me graph in the standard window. Option 6 is the standard window. The standard window always goes from -10 to 10 for x and y. It's a good window to have for most functions, but for this problem, it really stinks because I can't see the graph, right? So you have to, so the reason why I like this skill, because you're going to do this often in pre-calculus and in AP calculus, if you take, or even non-AP calculus, whatever class you take. You have to understand context. What do the variables represent? This is why people struggle with verb forms. They never understand the context. The context here. What is x representing here? Time. Time in what years? It makes no sense to do negative years, right? And after 22 years, they have 575 people. So if you want 800 people, maybe it might take 50 years, maybe it might take 60. I don't know. That's gonna be you're gonna have to ballpark it and mess around with it a little bit. Let's say 50, right? Actually, let's do 30 just to see what would happen. I'll do 10 here. Y was population. I don't have negative people. That makes no sense. I need to graph 800. Let's go 1,000 just so I could see y equals 800. So if I go 800 as the max, then the horizontal will be at the top of the graph. So I want to just have it somewhere in the middle. I'll go 100. So I only went from 0 to 30 for x, right? And here's what's going to happen. Do these guys touch?
No.
But not yet, right? So you have to be judicious about your window and say, well, let's make this bigger so I guarantee they touch. So you're going to have to play around a little bit. It's a skill set that we're teaching you guys. And you'll do this often in pre-calculus. There we go. And then how to find it, you hit this. Second trace. And clearly intersect. Because that's what we're looking for, right? By the way, that menu, trace is right by graph in the top row. Yeah, you guys are just learning. You guys are just scratching the surface of this calculator. This calculator does a lot of stuff. If you want to find the high points and low points, that might have been helpful for polynomials when you guys were doing that when I was on the fraternity leave, but We'll revisit this for sure.
The first zero, is it like the X?
That's intercepts. Or if you want to find particular Y value, do that. These last two are calculus things. You'll learn that when you get to calculus.
What about the Y intercept?
We're just playing 0 for X. You can use option 1 for that. So if I pick option 5, and it's going to ask you, Chan, go ahead. It might be bugging. I'll come back. Now, when I ask for a first curve, they say, where do you want the cursor to be on the first curve? Usually it's good to put close to the point of intersection. What the calculator is doing, it's plugging that number, that X value, into the first equation. And then when you hit the second curve, it's plugging that X value into the second equation, which I know is 800. And then it's going to try to find where the Y values converge. There's an algorithm this calculator uses where it plugs in both of these X values into each equation. And says, okay, they don't equal each other, let's plug in a larger X value. They don't equal each other, let's plug in a larger X value. And it keeps whittling its way down. And yes, exactly, until it gets the answer.
Wait, how do you?
And there you go. That's how you find it.
I'm so confused.
Hit second trace,
Yeah, I did.
option 5,
Yeah.
hit enter 3 times. But did you change your window?
Yeah.
Okay,
Oh,
what?
oh yeah, I got it.
Yeah. Okay, and Shan, I'll come check what's going on. Okay, one more problem, guys, and we're done. And then, as I promised, I'll put March Madness on. I know you're eager. Okay. Well, the last 10 minutes takes forever to. Yeah, I know. Okay. Okay, there we go. All right, I'll put it on. Last one here. Okay, same thing. But when the population decreases, you're gonna do this, guys. Okay. Guys, it's not talking about shaving. Yeah, all right. Percent decrease. Same thing, but you're doing minus because you're going down. Okay. So initial value. What's initial value for this species here?
No.
And it gets what will we expect population in the year 2000? So 1980. So R's 0.08. And how much time has passed? 20 years, great. So let's do it. Y equals 3000. 1 minus 0.08 raised to the 20th power. Now what's happening is you're doing 3000 times 0.92, which is less than 1.
Is that a minus sign? Oh,
That's a 0. Sorry, my handwriting stinks. I could do better. Sorry. Oh, thanks. Okay. So anyway, 0.92 is a number less than 1. What happens when you multiply something less than 1? It keeps getting smaller. Keeps getting smaller, right? So let's punch it in. If I punch it in, I do 3000 times 0.92 raised to the 20th power. And wow. So this species had 3000 as its population. In 20 years, it dropped down. So it's probably being hunted or poached, or we have reproductive issues or environmental climate change. I don't know, but it's kind of sad, right? So someone's got to step in. This is the species dying off. So after 20 years, it drops down to 5 or 6. Now, even more morbid, when there's only be 1 left of this species, and it's not supposed to be school population. That's we're not talking about humans. We're talking about just the species, not the school population. That's a typo. I forgot to change that. Let's find out. So 1 equals definitely more than 20 years for sure. Because in 20 years, it dropped to 566. We want the population down to 1. So how much more longer will it take to get down to 1? That's what we want to do. No, we're going to plug in the calculator. So you do 1 minus 0.08 raised to the t power. So what I'm going to do is I'm going to graph, go back to the same thing I just did. I'm going to change this to 3000. Oh, not 30,000, 3000 times 0.92 raised to the x power. Now I'll put 1. Now, when I graph it, let me change the window. So it might take 50 years, or maybe it might take longer. Let's do 100 years. I don't know. Now, this is not a good Y max, because I want to graph Y equals 1. I don't want to go from 0 to 1,000 and graph Y equals 1, right? Let's take it to 10. So I can at least see in the middle. Let's graph. So the exponential decay function is going to be coming soon. There you go. And Y equals 1 is right there. Find where they intersect. Second trace. Option 5. Hit enter 3 times. So it takes about 96 years. So if people don't do anything to save the species by the year, probably not in our lifetime, 2000, well, 1980 plus 1980.
76.
Yeah, I'll be like 99 years old if I'm still alive then. So anyway, 2076. Yeah, I was born in 1977. So. Yeah, we're all gonna be old. So when that happens. So hopefully you have good genes. Eat well, be happy, exercise. So 2076.
No, I think it was that.
All right, so that concludes the notes. So again, let me stop the video.